let us continue with our implementation of linear regression in a neural network setting. So far we were working with a simple model with a finite number of features, and we were predicting a continuous output. Here we want to look at a more general case where we have a high dimensional input with many features, and we are predicting multiple continuous outputs. We worked with this in previous machine learning and statistical learning setups, where we discussed the importance of variable selection or feature selections and applying regularization to prevent overfitting. So we are going to bring those concepts that we know in these setups of neural network. And like the previous lectures, this allows us to apply those techniques in a familiar setups. And later we will use the same techniques in a more complex architecture. We import the necessary modules and we set the seeds for reproduction. And then we are going to write a function that produces a synthetic data for us that we know it's ground truth. Okay, so I already wrote the function. It's basically the same Gaussian data generator, but here it is a multivariate Gaussian. So the default setting is it is producing a number of samples. Here, for example, 1000 sample, and with a lot of features. So here, for example, 100 features. So we have 5 outputs, and here I planted a hint that basically 10 of these features are the most important features, and I want my regularization to help identify these features. Okay, so basically this is a multivariate normal. It has a covariate structure, and it will return the 1000 observation, in this case, of X and Y, also the true weights of the linear model. Okay, so let's write down this multi-output linear regression model. We are initiating the class, and we have the input dimension, output dimension, and initialization scale for the weights, because in high dimension it's important where we start the weights, and default PyTorch init might be too large. So we have the super init and one linear layer, still without nonlinear activation because we are still doing linear regression. And this is the Torch-no-grad way of initialization of the parameters. So we add some print statements, and then we will write the forward method. So remember, the for method returns the outputs, where here we have multiple outputs. Okay, so let's write the duck strings, and then return the evaluation of the linear layer. So with that, we are basically done here for the class, since we will do the training outside of it. But like before, we are going to add another method to get the weight stats. So here we have a lot of weights. We don't want to print them one by one. So we are just going to print some statistics, including the norm of the weights, mean, standard deviation, max, and some measure of sparsity. And we are going to use the following stats. So maybe the weight norm, and we can add the weight mean, weight standard deviation, weight mean, max. Let's just use max, and maybe the weight sparsity. And we have to choose how to do this one. So the first view, we have already functions. So for the measure of sparsity, we are going to count the number of weights that are smaller than some threshold small value over the number of the entire parameters. With that, let's count the number of elements that are small, and then we divide it by the entire number of elements in the weight tensor. Okay, so with that, we are going to return the stats. Okay, so now we want to write a custom loss. If you remember, we had MSC before, but here I want to include some regularization penalties, including L2, L1, maybe a elastic net, which is a combination of the two. I assume that you know these concepts from before. And with that, let's write the class. Okay, so let's write a init class. Of course, the class will inherit the NN module. So let's specify this. Also, I'm going to add a debugging message to always log the hyperparameters here. With that, we want to write a forward method that computes this regularized loss. So we are writing the forward method, and here I'm gonna change this. And some dictionary here. So first, we have a base MSE loss that we know how to do it. So to compute the loss related to the L2 and L1, we're following the suggestion. Okay, with that, we can write the total loss. Which is this. Note that we could do this multiplication here. And if it was not because of the suggestion and me being lazy, I would do that. Let's write a debugging message that tracks the individual components and then return the loss and this component. So now I want to write a training code. Not only we need this regularization, we also need to introduce this validation set that allows for an unbiased validation of our predictions. So the nice thing about the validation set is it helps us to detect overfitting early, and it helps us to choose the optimal hyperparameters like those lambda values, and then decide when to stop the training. It is one way of avoiding the overfitting. So remember that sometimes, especially in high dimension where we have small samples, the validation loss is going to be very high compared to the training loss. And that shouldn't deter you, as this is very natural. Okay, so with that, let's write the function. And y train. So just like before, we're going to write the data loaders. Okay, so then next we need to do the criterion here and choose our optimizer, which is already chosen for us. Let's stick with our SGD for the sake of consistency. We want to track a few metrics, and then we can write the training loop for epoch in range. We have that. or the epoch stats. So we have the loss. Maybe we can even track MSE. And also the number of batches that are. So we need this to basically do some averaging. Okay. We can start the batches. You see that it's already here. So we have the optimizer that is now zeros. So this is the forward pass here. So the output of the criterion, if you remember, is the loss and components, which takes in this batch pred and batch y. And here, so we have to, let's check back the criterion, which is this class. Here, it takes in the NN module. So here, okay, so we inherit an NN module, and this is basically a generic NN module. Later, as you saw, we are passing our own model, but a loss function should be able to work with any architecture. Okay, so in the forward pass, we are working with the weights. So here we should enter the model. And here, again, here we are going to use the NN module because we can enter it later, right? So, okay, so with that, here we only work with weights, but this can include the biases too. So we have to make sure these parameters are only weights, not biases. So I'm confused why I got this suggestion. So let's go up. Okay, so we didn't initialize the biases. Bias is true by default. Okay, so now this is okay. And in that case, we have to specify here that we want to only cache the weights, not biases. Okay, so let's rewrite this. So we want to sum up these values only for the weights. So we have to write an if statement somewhere to check if the parameter is a weight or a bias. Okay, so let's start with and L1 loss to be 0, and then for loop that goes over the model parameters. But I also want to check if the parameter is a weight or a bias. So I'm going to check the name of the parameter also. Okay, so let's see this. Okay, this should be okay. So, okay, we prevented an error before happening, which is always good. So here, even before the backward pass, you can put some checks, like for example, if the loss is none or infinity, you can break the loop. I don't foresee anything happening here in this linear regression, but for larger and more complex networks, you may need to put these checks for nans or inf losses. Okay, so I'm gonna skip that. Also, let us also track the gradient magnitude. Before doing the step. Okay, so this is the total norm. That is summation of all of the squared norm values. And we can, of course, do a square root of it. And we can append it. So let's do the append at the end for all of them. Then we update the parameters, update the epoch stats. Okay, so that's that. We can also add the validation phase here. So for validation phase, we want to only evaluate the model. We are done with the training. That is done over the training data. And here for the validation, we are just going to switch to the eval mode. And then with Torch no grad, here, like I said, I don't want to work on the train. I want to work on the validation. So let's do it this way. We are doing over xval and same criterion. Okay, so with that, let's record the metrics, which is computed like this. So for each epoch, we want to compute the average training loss of that epoch. Okay, so that's that. And then average training MSE, weight norm, gradient norm. Okay, so, and then we can add an early stopping criteria. Wants to check if validation loss is not decreasing after like several consecutive epochs. For example, let's assume if after 20 epochs we don't see an improvement, we can stop the training. So if we have to have 20 epochs already gone, then here you see the history validation loss greater than that. And since I want the last 20, not just the last two, and then in that case, we print this out. You can put a if verbose here. And this breaks the training. We can, of course, continue more verbose, which we are going to need later for more complex networks, but I'm going to skip that. And I'm going to just return the history. Okay, so we can generate the data using what we wrote, splitting what we generated into 80% training, and the rest will be validation. It's important to standardize the data, of course. Here you see that we did the standardization, and it should be separate, the train and validation, to avoid any leak in our pipeline. And then here we create the model and we train the model. So doing that, we see that the training is stopped at 23. Basically, the first two epochs is enough. And our stopping criteria basically checks, and it saw that the next 20 is basically not improving anything. And you see that the validation over the training MSE ratio is pretty good, which shows there is no overfitting. And this is the case for a simple linear regression. But as you see, when we move on to more complex situation, the overfitting will be very common. And we will do that in the next lecture.